Section 13, question 2. A householder has a garden in the shape of a right-angled isosceles triangle. It's intended to put down a section of rectangular wooden decking at the side of the house as shown in the diagram. Find the exact value of ST. So we can see that ST is basically this brickwork base portion of the diagram. What we can also see is that this is a right-angled triangle, and the ST represents the hypotenuse. It's an isosceles triangle where that's 10 and that's 10. Well, I can use a bit of Pythagoras, and ST squared will be equal to, well, it's the hypotenuse, so remember for Pythagoras, the square of the hypotenuse is equal to the sum of the square of the other two sides. So ST squared equals 10 squared plus 10 squared. That means that ST squared is equal to 100 plus 100, that's 200. ST then would be equal to the square root of 200, and I'm going to simplify that third, and that would be root 100 times 2, bring that out, and that'll be 10 root 2, and that is part A, that's the length of ST. Part B, given that the breadth of the decking, as we can see here, is x metres, show that the area of the decking, which is this, the rectangle here, is given by 10 root 2x minus 2x squared. Right, well I can see that this is a right-angled isosceles triangle. Now, what that obviously means is that this angle in here is 45 degrees, as is this angle here, also 45 degrees. I can see that that's a right angle and that's a right angle. That tells me that this angle here is also 45, and this angle here is also 45. Meaning that as well as the bigger triangle here being a right-angled isosceles triangle, this is also a right-angled isosceles triangle, as is this bit. Now, if that's true, which it is, the breadth of the decking is x, so this is also x, which means this is x, and this is also x, since it's an isosceles triangle. So that's got a length of x there, and that's also got a length of x. Now, to find the area of the decking, it's going to be length times breadth. I've got the breadth, which is x. So to find the length, well, that's pretty straightforward now. The length of ST is 10 root 2. I then take off x and another x, and that will give me the length of the decking, which is 10 root 2 minus 2x. Now, to find the area of the decking, it's length times breadth, and that's now pretty straightforward. So the area will be given by 10 root 2 minus 2x times x. If I expand that out, that's 10 root 2 x minus 2x squared, and that's the result that I was looking for. Part C says, find the dimensions of the decking which maximises the area. So again, I'm going to look at the two options for that one, which is nature table and double derivative. But before that, I'll need to differentiate the function. So 10 root 2x is a constant x, that will just become the constant 10 root 2 minus 2x squared is minus 4x, and that is equal to 0. I'm going to bring that over, and that will give me 4x equals 10 root 2. X is equal to 10 root 2 over 4, and that can simplify down to an exact value of 5 root 2 over 2. So my two options are nature table or double derivative. So I'm going to first of all look at nature table. So it's x, a dash, and slope. My exact value is at 5 root 2 over 2. I can select neighbouring values to be 3 and 4. So for the gradient a dashed at 3, what I'll do at that point is to sub 3 into the differentiated function. So I'm just going to use a bit of space here. So that will be a dash equals 10 root 2 minus 4 times 3. That gives me a result of about 2.14, which is a positive result. I'll now sub in 4, so a dash equals 10 root 2 minus 4 times 4. The result for the gradient this time is approximately minus 1.86. Most important thing though is it's negative, and I can see that I've got a max turning point as expected at x equals 5 root 2 over 2. So for the double derivative, differentiate the function again, the constant will go, minus 4x will be minus 4, so we can see that there's no x value to sub in, but we've got a negative result as expected, so max turning point at 5 root 2 over 2, since a double dash, i.e. the double derivative, is less than 0. The question then asks me to find the dimensions of the decan which maximises its area. We've proved the maximising of the area at 5 root 2 over 2 for x, so the dimensions of the decan are the length and its breadth. So for the breadth, that's pretty straightforward, that's just given by x, which we've calculated to be 5 root over 2 to give the maximum. For the length of the decan given up here, we'll just take that 5 root 2 over 2 and sub it into here for x. So the length of the decan will be 10 root 2 minus 2 lots of 5 root 2 over 2. They two go, 10 root 2 minus 5 root 2, and that's 5 root 2, and that's the final answer to the question. It's important at that point to read the question carefully and to see exactly what it's looking for. Sometimes it just says find the value of x, but if it asks for the dimensions, you need to return to the diagram and pick out the pertinent information.